Hello everyone, this is Sam Lochterman with Datavolo, and today I'm going to walk you through advanced document processing. So the first step of any pipeline that we're building for a use case like this is going to be gathering our documents. And let's first take a look at what these documents look like. So we're going to be parsing some financial 10Ks today. And these documents are fairly complex. They have sections, they have narrative text, they have tables. It's very important that we get the integrity of these tables maintained as we chunk and transform these financial 10Ks. We're also going to see things like figures. So these are charts. We also want to be able to make this information useful for our downstream application, which is often going to require language models that can understand and describe these figures so that we can embed and retrieve those natural language descriptions. So let's take a look at what this looks like in Datavolo. So the very first step is going to be acquiring documents. In this case, our data is going to live in S3, but you can imagine these documents living in any document store as Datavolo ships with hundreds of different connectors for sources and targets. So this could be SharePoint, Google Drive, Dropbox, etc. We're first going to list the files, and we're going to use a specific strategy here to be able to recognize change in the future. We're going to track the timestamps of the documents that we process, and this is going to be really helpful as we want to be able to handle change for these documents. You can think about this as change data capture for unstructured data, and this listing strategy is going to help support that. After we've listed the data, we're then going to fetch these, and we're ready to do some additional parsing. So the key thing that's necessary for parsing here is to understand what these complex documents entail, and that's going to be all of that complexity that we saw in that Apple 10K example. We need to recognize what are the tables, what are the images, and what are the sections so that we can chunk things appropriately and send certain components downstream to other services. In this case, our model is based on YOLO-X, which is a computer vision model that has been fine-tuned and customized by us on data sets, which allow us to understand and derive these bounding boxes and these labels for all the different components of the document. We can take a look at what that looks like. We actually, within our provenance viewer, our UI now has this ability to take a look at these documents after we've done this labeling and bounding box derivation. So as I mouse over certain components, all of these different labels that we are seeing here, like this is a section, what page is this part of, whether this is inside of a specific container, what the confidence was of the model that drew that bounding box and that label, that's all easily available. And if we look at some more complex parts of the document, like the ones we were describing at the top, we see in this yellow bounding box, this table has been recognized with the right label, and we can then send this part of the document to the right downstream ML service for parsing. Similarly, on the next page, we have this figure that we recognized. This figure is now something that we can send to a language model because we've drawn the right box. We understand exactly what this is. Excellent. So that was a useful way to understand what the parsed output looks like, but behind the scenes, this is actually a JSON representation, and we're going to use that for a couple of different downstream use cases. In particular, once we have this representation, we're going to use that to chunk the document in a few different steps. We're also going to use that to do things like enrich this document further with other historical information. We can also use that to do things like data quality, to do things like PII redaction. So very powerful once we have that representation. All right, so one thing that we see here is we're routing different parts of the document to different downstream processors within our data flow here. So tables go to a specific place, images go to a specific place, etc. Let's take a closer look at what that looks like. So on the left-hand side of this flow, you're seeing a prompt OpenAI processor. The images are being routed to this processor so that we can send them to GPT-4o, which is a multimodal language model that's very good at understanding images and giving us natural language back. We're going to use that natural language to embed and retrieve for later so that we can build the right context around this part of the document. Similarly, on the right-hand side, we see that our tables are routed downstream to a different ML service. This is our table structure recognition service. This allows us to understand all the rows and columns in this table, to extract the right data types from the right cells, and make sure that when we chunk this document, we're not going to do things naively like cut that table in half. So then we will have the right data to retrieve in the right format when users are asking questions about any financial data in that table. They might be asking things like, help me understand how Apple's profits have been trending from this reporting period to the previous one. To do that, we really need to have the right financial data extracted from these tables within the document. Excellent. Once we have done this, we're now in a good position to merge everything back together. So Datavolo has extracted these different components of the document, used the right ML services to derive and extract the right content and context, and now we're merging all of those different pieces back together into a single representation. So that's very powerful. Our JSON that we're using behind the scenes to capture the nature of this document has now been fully populated with the right table structure and the right image descriptions. Let me zoom out and we'll continue down our flow here. So we often need to, as a data engineer, we need to extract important metadata in order to use that as a lookup to enrich this document with other information. So if we're talking about Apple, a single 10K is going to have lots of good information, but it's not going to be comprehensive in terms of the kinds of questions that users might want to ask and understand about Apple as a company. So imagine you have other historical data about Apple. The data engineer can extract the ticker symbol using a regular expression here, pulling that out of the title of the document or the body of the document. And they can use that as a lookup key to actually enrich this document further with that information we have at the company level about Apple. And this raises an important point about really understanding the use case, understanding the type of questions that your end users are going to ask, and building appropriate evaluation data sets that captures all of those questions. These evaluation data sets are what allowed us to understand that we needed to enrich this single document with information about Apple because users were asking questions that required that. All right, so after we've extracted the ticker symbol for a lookup key, we're going to store these chunks in S3. We're going to ultimately write this data to Pinecone, which is our vector database, and is going to support retrieval for our LLM applications, but it's also important to store the chunks themselves. For many advanced retrieval patterns, one that's pretty popular is called small to big. The idea is that you actually embed and persist different chunks of the document than what you might send into the language model for generation. This is because the data engineer is always trying to strike this balance between semantic precision to drive good retrieval and richness of the chunks to drive good generation. So there's a back and forth there. And by storing the chunks, because we have expressed this document hierarchy, we can actually figure out how to traverse this document graph and tie the small chunks back to the parents in case we need to use those for synthesis. All right, so let's talk more about chunking. This is one of the main steps that a data engineer is going to take when processing a document. And again, that's because we only have context windows that are so large. We only have embedding models that can input a certain amount of data. We have to be really smart about how we chunk things. And there's some experimentation here that we will see the data engineer goes through. We're going to use a recursive or two-step chunking process. The chunk document processor, which expects this JSON representation that I described, it's actually going to chunk by section using those derived annotations. So we have different strategies here. Because we have the section label from the computer vision model, that's going to be a really nice way to structurally chunk this document. And we can decide different options like whether we want to include subsections within that same chunk, what the max size should be, These are all different things that a data engineer will tune, and we'll see how we capture those different tunable parameters to support experiments and evaluation. All right, so this looks good in terms of the first level chunking, and at this point, after we've chunked the document, we now have text. So we can now do chunk text without that JSON representation. So now we're going to do things like sentence-based chunking and semantic-based chunking. As I zoom into the create final chunks process group, we're actually going to see many different chunking strategies. And this is really useful as a data engineer because what I ultimately want to do is A/B test different strategies and different tuned parameters against my retrieval scores that I'm going to get from my evaluation data set. So if I look at the far right side, when we're chunking text, we have different strategies. I can do things like sentence. That's going to be really good for precision. It's going to create a high likelihood that my query embedding is going to match my chunk embedding well, but it's not always going to have that richness that we talked about that's important for the generation step. So we might want to balance that, and to do that, we can do a different chunking strategy, which is semantic in nature. So what do we mean by semantic? Well, for every consecutive sentence, we're going to do a pairwise comparison using cosine similarity. When the similarity between consecutive sentences drops below our threshold, we're going to split there and call that a chunk. Now this threshold is another tunable parameter. So how did we get 0.6? Well, we experimented and we did evaluation, and we determined that as the data engineer, this is the best threshold to use, and now I can give a good retrieval set back to my AI engineer that's developing my front-end application. But for each of these different chunking strategies, we've determined that we can write to different Pinecone namespaces. This namespace is going to be expressed using this expression language, so we can dynamically capture which strategy we used. That way, when we do evaluation, we know exactly which strategies and parameters worked out best for retrieval effectiveness. All right, so we're in great shape now. We have chunks. What do we do before we write them to our Pinecone vector database? Well, we need an embedding model. So let's take a look at the write to Pinecone process group. As I scroll to the top here, the first processor I'll now use is create OpenAI embeddings. So we have different embedding models to use. This is again something that the data engineer might experiment with. They might use different models. They might try to fine-tune an embedding model, and Datavolo can help you build and express those fine-tuning data sets, just like we can help with constructing evaluation data sets. In this case, we're using OpenAI. You could also use local models, ones that you might have acquired from Hugging Face or tuned for your specific vocabulary. If we take a look at provenance for this example, we can see what this looks like before and after the embedding. So before embedding, we just have text. This is the output of that semantic chunking. And on the output claim, now we have the embedding weights as well. So these are all capturing how this chunk was embedded into the embedding space, and this is going to be useful when we try to match queries against similar document chunks. Perfect. So after we have computed our embedding weights, we now have a really important step of setting the chunk metadata. So before we write this data to our vector database, we want to make sure that we've captured all the important context about this chunk. This is really useful for things like hybrid search, where we're going to use these dimensions to filter our result set before we do semantic similarity searching on those embedding columns. And secondly, we can also use this metadata to do things like ranking the data. It's important that we send the chunks in the right reading order to the language model as well. The other thing this can be useful for is things like compliance. So if you think about GDPR, for example, where I might need to delete all the data I have about a specific customer, well, I should have a good way to trace back a chunk to the customer that the parent document is associated with, so I have that lineage. And by using Datavolo's powerful end-to-end lineage capabilities, along with the sourcing of metadata and context from across all these different systems, we have exactly what we need to achieve that sort of compliance use case as well. And so at any step in the flow within Datavolo, you can always go into provenance, you can go into lineage, and you can see exactly what has happened with this flow, and you can even see what that looks like over time as things have changed. Very powerful capability. All right, so I mentioned change data capture for unstructured documents and data. One of the ways that we're expressing that is we are deleting the write vectors from Pinecone before we do this upsert process. So I'll skip over some of the details there, but you do need to delete chunks that you've seen before, and really, as new versions of a document come in, you really just want to modify those chunks that have changed. Also, sometimes note that it might just be the metadata that changes about the document, and you want to leave the vector weights alone, but make some of the changes to that dimensional metadata. All right, so the very last step of this is to upsert this data to Pinecone. We're doing a combination of update and insert with this logic, and we're writing to a specific index. Now note that this namespace is, again, using expression language. That's powerful because our data engineer has divided up the different embeddings into different chunking and parsing strategies, and by storing those in different namespaces, we enable the evaluation that I described. All right, I just wanted to conclude by showing you what this looks like in Pinecone. So this is that 10K processing index that we talked about, and we have 6 different namespaces within this index. These are combinations of different chunking, parsing, and tune parameter strategies. And then for a given namespace, like 10K sentence, if I expand this specific embedding, or the specific vector, we can see all of the metadata that we captured. So we have the title hierarchy, which was derived from our computer vision model. We have the original URL that is associated with this document, which is important. We have additional metadata that we've used to enrich this document. We have the full content, and of course, we have those embedding weights. So now the AI engineer has everything they need to complete the AI application development, and they can be confident that their retrieval system is going to work well because the data engineer has done all of the right things to make this unstructured data useful for AI. Thank you very much.